Is ours the only universe? Or are we part of an infinite and boundless expanse of parallel realities, a multiverse in which infinite versions of ourselves are living every imaginable life? This is not just science fiction, but a serious scientific theory, one of the most profound and controversial in modern physics. An idea that forces us to rethink everything we think we know about reality, space, time, and even our own consciousness. If you want to find out what science says about this shocking possibility, then stay with me until the end. And if these journeys to the frontiers of knowledge excite you, subscribe to the channel so you don't miss the next explorations. The concept of the multiverse, beyond popular representations, hypothesizes the existence of other universes outside our own. These would not necessarily be copies of ours with small differences, but could have completely different physical laws, constants, and even dimensions. The idea of a plurality of worlds has ancient roots, but it was only in the 20th century that it began to take a scientific form. Today, the scientific foundations of the multiverse rest on two major pillars: cosmology and quantum mechanics. The physicist Max Tegmark has proposed a classification that includes 4 possible types of multiverse. T-Type 1, universes with the same physical laws but different initial conditions. Type 2, universes with different physical constants. Type 3, universes derived from the many-worlds interpretation of quantum mechanics. Type 4, universes with different basic mathematical structures. The Level 1 multiverse is the simplest and least controversial. It is based on 2 ideas. The first is that the universe is infinite, or vast, much larger than what we can observe. The second is the ergodic hypothesis, which states that given an infinite space, every possible configuration of particles will sooner or later be realized. Our observable universe, called the Hubble volume, is the sphere of space from which light has had time to reach us in 13.8 billion years. But if the total space is infinite, then out there, beyond our cosmic horizon, there are infinitely many other Hubble volumes. By pure statistical probability, somewhere, there will exist a volume identical to ours, with another Earth and another you. The Type 2 multiverse is more speculative and arises from the theory of chaotic cosmic inflation. This theory suggests that immediately after the Big Bang, the universe underwent exponential expansion guided by an energy field, the inflaton. According to physicists like Andrei Linde, this process did not stop uniformly everywhere. Due to random quantum fluctuations in some pockets of space, the inflaton's energy decayed, inflation stopped, and a bubble universe like ours originated. In other regions, however, inflation continues eternally, generating a constantly expanding oceano that continually produces new bubble universes. In each bubble, the way in which fundamental symmetries were broken during cooling could be different, giving rise to different physical laws and fundamental constants. The Type 3 multiverse is even more radical and is based on a fundamental idea: quantum mechanics. To solve one of its greatest mysteries, physicist Hugh Everett proposed the many-worlds interpretation in 1957. In the traditional view, when we measure a particle in quantum superposition, its wave function collapses randomly into a single state. What happens to the states that were discarded by the collapse and their associated energy remains a mystery. He many-worlds theory offers an elegant solution that saves the principle of energy conservation. The other possible states do not vanish, but continue to exist in other universes that have just separated from ours. The crucial point of Everett's theory is that it reintroduces determinism into quantum physics. The collapse never happens. The supposed randomness we observe is just an illusion. When we make a measurement, the universe does not randomly choose a result. It branches, and all possible results occur, each in its own branch. But this theory works? The greatest achievement of the multiverse concept is that it offers an elegant explanation for the so-called fine-tuning of the universe. The physical constants of our cosmos seem calibrated with astonishing precision to allow for life. In a multiverse, with infinite universes endowed with different constants, there is nothing surprising in the fact that we find ourselves in one of the few that allow our existence. This is the anthropic principle. As for evidence, there is currently no direct and definitive evidence, although, as explained, the existence of the multiverse seems not only a possible, but also a probable consequence of the physical laws of the world we know. The philosophical consequences of a quantum multiverse are dizzying, especially if we think about the impact on our consciousness. To explain it better, let me introduce a rather brutal but certainly effective thought experiment: quantum Russian roulette. Imagine a quantum gun whose trigger is connected to a quantum event in a superposition of two states, one where the gun fires and one where it does not. At the first click, the universe divides in two. In one branch you die, in the other you survive. Your consciousness, by definition, can only continue to exist in the branch where you survive. From your point of view, you will pull the trigger infinitely, and the gun will seem to never fire, making you appear subjectively immortal, while there will be a multitude of universes where whoever is shooting will see you die. This, it should be reiterated, is only a speculative thought experiment that illustrates the extreme consequences of the theory, but certainly not something scientifically proven or to be replicated in any way or for any reason. If every quantum event creates new ramifications, then there are infinite versions of you. Personal identity would no longer be a straight line, but a constantly branching tree. Such a radical theory could only generate an intense debate. The scientific community is deeply divided. On one side, we have the critics. Nobel laureate Roger Penrose is one of the most authoritative. His criticism is technical and profound. He argues that the theory of inflation, and thus the bubble multiverse that derives from it, does not solve the fine-tuning problem, but simply shifts it to the initial conditions necessary to start inflation itself. He calculates that the initial state of the universe had to be so incredibly ordered and low entropy that inflation cannot explain it. Another critical voice is that of Federico Fagin, the inventor of the microprocessor. His approach is more philosophical. He considers the many-worlds interpretation to be science fiction, based on an overly literal interpretation of the mathematics. Fagin supports a view in which consciousness is a fundamental phenomenon of reality and not its byproduct. For him, the idea that the consciousness can simply branch with the universe ignores the inner and irreducible nature of the subjective experience. On the other hand, there are equally illustrious supporters. Michio Kaku, a well-known theoretical physicist and popularizer, sees the multiverse as the most logical consequence of our most advanced theories, such as string theory. For Kaku, the multiverse is not an option, but almost a necessity to make sense of modern physics and to elegantly explain the problem of fine-tuning without resorting to a divine designer. Other physicists like Andrei Linde, Max Tegmark, and Brian Greene are among the main architects and popularizers of these ideas. An fascinating position is that of Robert Lanza, a physician and scientist who has proposed biocentrism. For Lanza, the multiverse is real, but its existence is linked to consciousness. He argues that it is life that creates reality, space, and time. It is a vision that inextricably links the many worlds interpretation to the centrality of consciousness. In conclusion, where does all this leave us? The theory of the multiverse is one of the most powerful and suggestive ideas ever conceived. It arises from consolidated pillars of modern physics and offers solutions to profound enigmas. But, as the debate shows, it is not yet fully accepted. Its biggest limitation is the lack of direct experimental evidence and the difficulty of being falsified, which places it, for some, on the margins of science. It remains a fascinating, mathematically elegant hypothesis that forces us to confront the possibility that our entire reality is just a grain of sand on an infinite cosmic beach. It is a reminder of how vast the unknown is, and of how the pursuit of knowledge always pushes us to look beyond the horizon of our world. Thank you for traveling with me to the edges of reality. If you liked the video, leave a like, share it, and let us know what you think in the comments. A la próxima.